So, good afternoon, students. Yesterday we have started with the one-way ANOVA, and not exactly one-way ANOVA. We have started with the analysis of variance ANOVA, and we have gone through with the introduction as well as some of the terminologies basically used in ANOVA. So today we will be completing this ANOVA in this practical class. So either we will be having one session, or if the time requires, then we will go with the two sessions. Okay. So in the first session, we will be taking up the one-way ANOVA. And in our last lecture, when we were discussing about the types of ANOVA, so we have discussed that when there are one explanatory variable is considered against the response variable, then it is known as one-way ANOVA. Okay. So today we will take up the practical aspect of one-way ANOVA, that how to partition the variance and find out that whether the effect of the explanatory variable is actually causing any significant effect on the your response variable or not. Okay. So we have learned about the one-way analysis of variance ANOVA, and it is used for testing the equality of means of more than two populations. So when it is the case of two population, then we go generally with the t-test. But when it comes to the testing the equality of means of more than two populations, then we go for ANOVA. Okay. So when the observation in an experiment are classified with respect to single criteria, right? So if there is only one single criteria of classification of the observations, then we go with the one-way ANOVA. Okay. So that is, we are interested in studying the effect of various levels of one factor or one treatment. Okay. That is, what we want in our this analysis is that whatever the observations we are observing at different levels of treatment, that is one factor, what is the observations we made on the dependent variable. Okay. So for example, we can apply ANOVA for testing the hypothesis that five varieties of wheat, here the wheat is a factor, produce equal yield. That is, varieties of wheat are here factors. Okay. Produce equal yield. What is that yield? Yield is the dependent variable, isn't it? Okay. So on an average, or for testing the stress level of employees, for example, so here the stress level will become your factor. That is, employees in higher stress level, medium stress level, or low stress level. So your stress level will become your factor, and whatever the response you will be getting, okay, so that will be your this dependent variable, and so on. So simply in one-way ANOVA, we divide the total source of variation into two components. Okay. So there is a total source of variation is there. Whatever the data you will be getting, there will be some variation, and that has to be divided into two components. One is between groups, that is the due to treatment or due to the assignable causes, that is the first one, and second is within groups, that occurs due to chance or error or random causes. Okay. So these are the two components into which the total source of variation is divided in one way. Okay. So now we will be discussing with the model of one-way ANOVA, right? So in one-way ANOVA, the response variable y. So what I should do here is that before describing this one-way ANOVA, let me take you with some basic assumptions and then example. So I will just correlate this example with the that of the model, okay, whenever it is required, okay. So that thing will be more easier for you to understand that what I am talking about, right? So basically, let us first discuss the basic assumptions of one-way ANOVA. So following are the basic assumptions of one-way ANOVA. So first one is dependent variable, okay, is measured on interval scale, right? That is it is a scalar quantity, right? Then k samples are independently and randomly drawn from the population. So how number of groups you are making, so those groups are considered as different samples and they are drawn randomly from the population, right? Then population can be reasonably to have a normal distribution. So the population from which you are taking the samples should be normally distributed and all these samples should have approximately equal variance and various effects are additive in nature and your error component, okay, that we have discussed in yesterday class that when we will be calculating the value of y based on our model, so there is some error is there. So those errors should be independently identically distributed normally with mean 0 and variance sigma e square, right? So these are the basic assumptions of one-way ANOVA. Now, when we discuss the step-by-step computation procedure for one-way analysis of variance for k independent samples, okay? So the first step of the procedure is to make the hypothesis, okay? So what we have to do is we have to make a null hypothesis and we have to make a alternative, right? So we want to test the equality of population means. Say for example, there are k groups are there, okay, between which we want to analyze, okay. So what we are saying in our null hypothesis that their mean of these groups are equal. That is, there is homogeneity, right? And its alternative hypothesis will be that their means are not equal, okay. So this is alternative. So as for now you leave this thing, okay, this I will make you understand later on, right? So now we will try to understand the general procedure for testing hypothesis uh, using ANOVA with an example, right? So let us take this first example. There is some group of companies there, say for example future Group, which wishes to enter the frozen shrimp market. Okay, so they contract a researcher to investigate various methods of group of shrimp in large tanks. Right. So the researcher suspect that temperature. So what he suspected that temperature of the tank, temperature of water, right, is one of the important factor that influences shrimp yield and conducts a one-way analysis of variance with their level of temperature. So that is each combination of yield for each identical gallon tanks, that is the volume of the tank remains the same, okay. So the recorded yields are like this. So what he has done, he has taken the three tanks and in these three tanks, in first tank the temperature was 60 degree Fahrenheit. In second tank the temperature was 670 degree Fahrenheit and in third tank the temperature was 80 degree Fahrenheit. And this is the tank 1, this is the tank 2, this is the tank 3, right? So when in these tanks, when the temperature was 60 degree Fahrenheit, so the yield was like this. If similarly, these three tanks means three observations for this 70 degree Fahrenheit, the yields are like this. And when it is 80 degree Fahrenheit, the yields are like this. So we have this table that is temperature 1, that is 60 degree Fahrenheit, okay, then 70 degree Fahrenheit and then 80 degree Fahrenheit. It has three observations, right? Three tanks are allotted to this 60 degree Fahrenheit and these tanks have this yield 3, 5 and 4, okay. Then 70 degree Fahrenheit, the yields are 11, then 10, and then 12, then 16, then 21, and it is 17. So what you should observe here is that our response variable is, what is our response variable? Our response variable is nothing but the yield, isn't it? Okay. And our x, that is the factor on which this response variable is dependent, or this is also called as independent factor. Okay. Our independent factor is nothing but the temperature, right? So there are three groups. That is, one group is those are reared at 60 degree Fahrenheit, other group is those are reared at 70 degree Fahrenheit, and the third one is the those are reared at 80 degree Fahrenheit. Now we want to test the null hypothesis that the mean yield of shrimp at 60 degree Fahrenheit is equal to the mean yield at 70 degree Fahrenheit is equal to mean yield at 80 degree Fahrenheit. If these would have been two groups, then we may conduct a t-test simply. But now because there are three groups, okay, from the shrimp, from the same population, okay, but being subjected to different temperatures. So now we will be applying one-way analysis of that, right? So how to apply that one-way analysis of variance? So this thing we already have, this all, okay? So what we will be doing, we will be making a total, right? So all these are statistical notations, okay? Which means what we have to do in this, we have to total all the yields available at 60 degree Fahrenheit. So these all constitute your 12. Then the total of these three will be 33. Okay, these three will be 33, and the total of these three will be at 80 degree Fahrenheit will be 54, and the grand total will come out to be 90, isn't it? Okay, so now when you will be uh, taking the mean yield, that is mean, okay, so this 12 divided by 3, it came out to be 4. Then this 33 divided by 3, this came out to be 11. And this 54 divided by 3 came out to be 18. So what our hypothesis is that the mean yield 4 is equal to mean yield 11 is equal to mean yield 18 at 5% level of significance. Okay. So this is what we have to test. So how to do that? So up till now we have been given with this table, okay, three factors: temperature, 60 degree Fahrenheit, 70 degree Fahrenheit, 80 degree Fahrenheit. What we have done till up till now is we have made a total of these, then total of these, then total of these, okay, and taken the mean, these three means, okay, this much we have done, and this is the grand total, okay. Now our first this step will be, then this is our first step, that is one way classification. So we have classified our data in one way, okay. Now our second step will be setting up of hypothesis. So the small differences between sample means are usually present, okay. So the objective is to determine whether these differences are significant, that is what we are seeing this 4, 11 or 18, whether whatever difference there are, whether these differences are significant or not significant, okay. Or in other words, are the differences more than what might be expected to occur by chance? That is, whatever difference you are observing, whether they are just by chance or whether they are there in the population. Okay. So if the differences are more than what might be expected to occur by chance, you have sufficient evidence to conclude that there are differences between the population means at different levels of factor. Okay, so what will be our hypothesis? That population means of k level of a factor are equal, and opposite will be alternative. At least one population mean of a level of a factor is different from the population mean of the other levels of factor. That is, at least one of the mean is differ from other. Okay, so that constitute your alternative hypothesis. Okay, so now our first step, further step will be to make a square table. Okay, so whatever table being given to you, this is your third step, and third step is that you have to make a square table. Okay, so what's there in a square table? If you see that we have this 60 degree Fahrenheit. Sorry, I will write from here. 60 degree Fahrenheit. Then we have your 70 degree Fahrenheit. Then we have 80 degree Fahrenheit. Right? Then this is the, say for example, tank 1. So whatever value was given to you, okay, you have to square it. Okay, so 3 threes are there are 3 was given, so it will become 9. Okay, so 3 will become your 3 threes are 9. Then this 5 will become your 25. Then your 4 will become 16. And now you have to, what you have to do is that you have to total them up. Okay, what you have done earlier, so it came out to be 50. Similarly, it was given 11 here, so it will become 121. 10 here, so it will become 100. 12 here, so it will become 144. Now you have to total them up, so it will become 365. Similarly, 16 came out to be, the square of 16 is 256. Then square of 21 is 441. And square of your 17 is 289. Okay. So when you will total them up, so it will came out to be 986. Okay. And the total of these total, okay, that is if you total all of them, these squares, so you will get your row totals. Okay, that is 1401. Okay, so now further step. So first of all, what we have seen here is that your n number of observation are 9. Okay, then second thing you have to do is what is your grand total. So grand total we have already taken here, that is the sum of all the observations, so that is equal to 99, right? Then comes your correction factor, so you have to find a correction factor. So what this correction factor is equal to, it is nothing but grand total square divided by n. So it will become 99 into 99 divided by 9, so it will be equal to 1089. Okay, now, once you have this correction factor, then from square table you have raw sum of squares. Okay, RSS. So this is equal to 1401. This is what we have done here. That is, we have squared them all, and then this came out to be 1401. Okay. So now this is your raw sum of square. Okay. Now what will be your total sum of square? Next step will be to find out the total sum of square. Sum of squares. That is ESS. That will be raw sum of square minus correction factor. So what was raw sum of square calculated was 1401 minus 1089. So it came out to be your 312. So your total sum of square comes out to be 312. Okay. So this is your total sum of square, and this was your raw sum of square, and earlier we have calculated this your grand total number of observations and correction factor. Okay, this much we have done. Now we have to calculate next, in the ninth step we have to calculate your sum of square due to temperature. That is one of the factor is temperature na, that we have to calculate. So what you have seen is that these were the total of the at 60, at 70 and at 30. Okay, divided by the number of observation making them. Okay, that is 1, 2, 3. This is the result of the 3 total. Okay, so what you have to do is that you have to first square that value and divide it by the number of observation from which that total has been made. So 12 is square. Okay, if I show you here, so we were having these three values, that is we were having this 12, then 33 and then 54. Okay, so what you will be doing, that 12 square divided by 3, then 33 square divided by 3. If say for example this 12 is the result of 4 values, one more values is here, 1, 2, 3, 4, then it has to be here, it has to be, then here it has to be divided by 4. But because it is made up of 3 columns, okay, columns are 3, this C corresponds to columns, so it is divided by 3. Okay, so 12 square divided by 3, 33 square divided by 3, then 54 square divided by 3 minus correction factor, which we have calculated earlier. Okay, so our correction factor was 1089. So now we will solve this. When we will be solving this, so your sum of square due to this treatment, or this here your treatment is temperature, so that will be equal to 294. Okay, total sum of square came out to be 312 and sum of square due to temperature came out to be 290. Okay, now in the next step you have to calculate the sum of square due to error. Okay, sum of square error is very easy to calculate. What you have to do, total sum of square minus sum of square due to this temperature. So what was that, 312 minus 294, so it will came out to be 18. Okay, now our next step will be, so now you remember these three values. Okay, that is total sum of square, sum of square due to temperature, and your this sum of square due to error. Okay, because in this one way ANOVA we have to calculate the variation due to the assignable cause, and rest of the things will go into the error chance. Okay, so now next step, our next step will be to form a ANOVA table. So how to form that ANOVA table, this is important. So now we will be doing ANOVA table. So first thing will be your source of variation. So your source of variation, what was the source of variation in the three tanks? Although everything, your volume was equal, your shrimp were taken from the same population, the source of variation was the temperature of the water. Okay, so first is your temperature. Okay, so first one is your temperature. Okay, then this is the your assignable cause. Now all other things will go into error. This your assignable cause and unassignable cause will constitute your total. Okay, so your source of variation in your ANOVA table can be divided into assignable causes. Okay, this assignable cause temperature, unassignable causes, and the total. Okay, so what will be your degrees of freedom? Next column will be of degrees of freedom. So here the temperature you have to row minus 1. So what you have to do is row minus 1. So how many rows were there of temperature? 3 rows were there. So it will be equal to 3 minus 1 is equal to 2. Okay. Then what will be your total? Total will be your n minus 1, which is equivalent to 9 minus 1 is equal to 8, and your error component will be n minus r, that is total minus number of rows. So that will be equal to this 8, sorry, this has been written here 8 minus, not 8 minus 2, this is equal to 9 minus 3. Okay, so this n minus r will be equal to 9 minus 3 is equal to 6. Okay, so this is how we calculate the degrees of freedom. How this come? So here I will tell you that this if I subtract the this degree of freedom from the total, so you will get the error, that is n minus 1 minus r minus 1. So it will be equal to n minus 1 minus r plus 1. So this will cut out and this will be equal to n minus r. So this is how we get the degrees of freedom of the error. Okay. So now your this was your first column, this is your second column. Okay. Then comes your sum of squares. Okay, so first will be your sum of square due to temperature, so that we have already calculated. So what was that? That was 294. Then sum of square due to error was 18, and total of this will be 312. If you add 294 plus 18, it will become 312. Then comes your next column of the ANOVA table is your mean sum of square, MSS. So this is nothing but sum of square divided by degrees of freedom. So it will be 294 divided by 2, it will be equal to 147. Then this 18 divided by 6 will be equal to 3. Okay. Now next column will be your F ratio. And F ratio is nothing but your mean sum of square due to assignable cause divided by mean sum of square divided by your unassignable cause. Okay, so that will be equal to 147 divided by unassignable cause by 3. So it will came out to be 49. Okay, so this is how we make the ANOVA table. Now from this ANOVA table, the tabulated value, if you go with the F table, okay, which we have discussed in our earlier lecture when we were discussing F test, at 2 and 4 degrees of freedom at 5% level of significance, the critical value is 10.649, which is less than the calculated this value 49 for testing the significance difference in the shrimp yield due to differences in the level of temperature. So our null hypothesis is rejected. And what was our null hypothesis? Our null hypothesis was that the mean yield of shrimp in at different temperature is same, that is there are no differences, but now it is rejected. Hence there are differences in shrimp yield due to temperature at 5% level of significance. So this is our inference. Now we have three pairs. Okay, now we came to know that there are differences between the mean, but we do not know that which at which temperature differs from other. Okay, so once we are through with this thing, then we have to apply the t test. Okay, So again we have to apply the pairwise test in the ANOVA, and for that we will make that our this null hypothesis will be that this there are no differences, and our alternative will be that there is means the means are equal, and our alternative will be that the means are not equal. So our test statistics will be calculated like this: p value, that is we have mean value for two pairs. Okay, so our t value, t statistics will be equal to this first sample mean minus second sample mean, okay, divided by whatever this MSSE you got, that is mean sum of square due to error in the ANOVA table, okay, into 1 over that is number of observation in first group plus number of observation in the second group. Okay, so basically if I take this here, okay, so this value, that is yi minus yj, will be equal to t value into MSSE into 1 over Ni plus 1 over N. Okay, that is the first group number, second group numbers. Okay, so basically, therefore, if your difference in the mean came out to be greater than t value, t table value at, that is Ni minus 1, Nj minus 1 degrees of freedom, okay, that is Ni minus 1 into Nj minus 1 degrees of freedom and alpha by 2 level of significance. Okay, so this constitute your, this part constitutes your critical difference. Okay, so if your critical difference calculated here and your differences are greater than that critical difference, then your null hypothesis is rejected and there seems to be difference in the mean E. Okay, so what we will do here, that for all we were having n, I, n, j or whatever the value, we have 3. Okay, so everywhere this n will be 3. So therefore this cd, so this value, this t value at this ni, nj, this this degrees of freedom will be equal to 2.776. Okay, that is at 4 degrees of freedom, and this MSSE is equal to, we have calculated 3. So this 3 into this will come out to be 3 by 2. So this 2 will go upside. So this 2.776 into 1.44, it will be equal to 3.997. So our critical difference came out to be 3.997. So if you subtract the this second mean from the first mean, so this y1 minus y2, okay, that is we have calculated the mean here. So it was 4, it was 11 and 18. Three means were y1 was 4, y2 was 11 and y3 was 18. Okay. So if you see these three, so I will answer your question. Shreya Mishra is asking something. So this y1 minus y2 is, this 4 minus 11 is 7, then 4 minus 18 is 14, then this 11 minus 18 is 7, which all are greater than 3.997. Hence our null hypothesis is rejected, and we can say that these mean 4, 11 and 18 differ significantly from each other. So therefore there is a significant difference in shrimp yield at three different temperatures. Okay. So one question was asked by Shreya Mishra, and she was asking that whether the tabulated value of f will be taken at 2 and 6 or 2 and 4. Yes, it will be calculated at 2 and 6. There is a misprinting. Okay, because this is 6 and this is 2. Okay, so what we have to do is that we have to see this value at 2 and 6 degrees of freedom. Okay, so that I will correct afterwards. So whatever the value will come, I will replace in the original notes, and because this 49 is going to be higher than that, so our null hypothesis will be rejected. So this completes our one-way ANOVA. And what we have seen is that when there is one factor is there, say for example here temperature has been given and it has more than two groups, then we can apply the ANOVA, and there are simple steps of calculation for this sum of square, grand total, correction factor, and accordingly we can make this table from which this F value can be calculated. And if this F value at given degrees of freedom is greater than the table value, then this factor is significant and hence the means are different. Okay. Then for pairwise comparison, we can go ahead with the t-test using this formula, and this MSSE component will come from the ANOVA table itself. Okay. So this is how we do the pairwise comparison also in ANOVA. Okay. So I will correct this thing. Thanks Shreya Mishra for correcting me that this will be 2 and 6 degrees of freedom. Okay. So this is all for the first session. In the next session at 4 o'clock, we will be taking up your two-way ANOVA. Okay. So till then you can take rest and you can also revise. So thank you very much. Thanks for your patience here.